A wave is smeared out through space. That is, its location is not precisely defined. Since matter exhibits wave characteristics, there are limits to how precisely we can define a particle's, for example an electron's, location. Think about a wave on the surface of a pond. Where is it? Well, it's kind of all over the surface of the pond. It's here, it's there, it's kind of everywhere. Matter has these wave-like properties, and because of that, there are limits to how precisely we can say exactly where something is, particularly something very small like an electron. This limitation, besides applying to a particle's location, also applies to a particle's momentum. Which brings us to Heisenberg's uncertainty principle. Not that Heisenberg, that Heisenberg. The uncertainty principle reads something like this. It is impossible to know simultaneously both the exact momentum of a particle and its exact location in space. There's an equation that goes with Heisenberg's uncertainty principle. Here it is. Often it's represented as the delta terms mean uncertainty in. So what we have here in this equation is basically the uncertainty in the location, that's what delta x means, multiplied by the uncertainty in the particle's momentum is greater than or equal to Planck's constant divided by 4 pi. There are other ways to represent it, but that's one way. What we're saying here, in short, is that although we think of electrons as solid particles, it is an oversimplification to imagine an electron as a solid particle moving in a well-defined orbit. Electrons, like waves, are kind of spread out over a larger space than we sometimes think electrons as taking up. Let's give an example here. There's a trade-off with regard to our ability to know where a mass is and how fast it's moving. An electron, for example. Where is it and how fast it's moving? When I was being trained as a teacher, I heard this example and I've never forgotten it, and I think it's pretty good. If you can imagine this for a moment. You're in a very large room and it's very quiet. And in that room there is a ping pong ball somewhere. Let's say it's a classroom. And this classroom is totally pitch dark, no safety lights, no lights from the hallway, totally dark, you can't see anything. And you know that there is a ping pong ball in there. So you're in the room and you listen and you hear absolutely nothing. How well do you know the ping pong ball's velocity? That is, its momentum. And the answer is you know it pretty well, because you don't hear any ping pong ball rolling across the tile floor. So you have a pretty good idea of what its momentum is. In other words, the uncertainty in the momentum is very small. However, your uncertainty as to where it is in the room is very large. It could be anywhere in that room. The uncertainty for where it is very large. The uncertainty as to how it's moving is much smaller. And there's a limit to how big one can get compared to the other. Now, let's say you're kind of feeling your way through the room and you have your hands on the desks, you can feel them, you can't see them of course, and suddenly you bump the ping pong ball. It falls off a desk and you hear it bouncing on the tile floor. Now what? Well, the uncertainty in where it is has gotten much smaller. But the uncertainty as to how fast exactly it's moving has now increased. There's a trade-off between how fast it's moving and where it is. If we read here in the middle of the screen, if we are pretty darn sure about its speed, then we're not very sure about where it is. This is, for the example, when you're in the room, you don't hear any ping pong ball, you're pretty darn sure about its speed. Its speed is basically 0. But we are not very sure at all about where it is. the uncertainty as to where it is very large. The uncertainty as to how fast it's moving is relatively small. On the other hand, at the bottom of the slide here, if we're pretty darn sure about its location, in other words, after we've bumped it, we're pretty sure about roughly where it is, then we're not nearly as sure exactly how fast it's moving. So you can see that the uncertainty in where it is has decreased, but the uncertainty as to how fast it's moving has increased. There's a trade-off there, and you can't know with certainty both at the same time.